rock, and you get this nice straight piece, straight edge piece that's been cut through the activity of these seeds doing hydraulic pressure. So in these cracks in the rocks that we've got, we have both the roots exerting this hydraulic pressure, plus if I've got any of these compartments here and seeds get into those, they can force those apart. And now what I've got is a process of the breaking apart of bedrock material into smaller and smaller pieces of rock, and soil is basically small pieces of rock with some humus in it, right, some detritus. Okay? So the idea is I move from this bare rock, the first group of species that shows up here, let's call that Seer A1, the algae, fungi, and bacteria. I could also get some lichens showing up. These can grow on rock. They also etch away at the rock. And then I would get some kind of plants moving in that are seed plants that can help to crack open the rock. And eventually I get to this group of pioneer species that show up once the soil has been formed. Now when I was your age, it was pretty routine to talk about this process as taking hundreds of years. That to convert bedrock into usable soil for plants, you're talking about 100 years worth of growth here. Then Mount St. Helens happened. I think we mentioned Mount St. Helens before when I was talking about a natural experiment occurring that people could use the results of. The volcano erupted and magma went everywhere and basically converted this nice forest into a bunch of rock, right? And people said, oh God, it's going to be hundreds of years before we have any plants growing back on Mount St. Helens. But the reality is, within the first year, we had this process, and within the second year, lots of plants had showed up, these early colonizers that are actually very good at existing within rock material. They just need enough of a nook or cranny to grab onto with their roots to keep from blowing away. And once you have them there, they help stabilize the area and allow for other species to move in, and then you get the accumulation of this detritus, this organic material, etc. You can kind of see that here. When the glacier receded up here in Glacier Bay, that's not really nice soil. It's a bunch of chips of rock. But this plant here, that's dwarf fireweed, can actually grow in this kind of material. Okay, so the new thinking is that this primary succession, it's not hundreds of years, it's a few years. In which case it fits in nicely with the regular timeline we have for facilitated succession. Okay. All right, so our first model here is facilitated succession, right? And then as part of that, we could talk about a primary succession model pre-soil, and then we can also talk about a secondary succession model where we've cleared the area back down to soil and then things restart again. Okay? Now, the fact that we've got facilitated succession and not just succession should suggest to you that there are lots of other models for succession, and there are. What we're going to do is talk about those now, but before I do, is just remind you that people, when they first started working with successional models, worked with old fields, and therefore there's a huge bias in ecology towards secondary successional models, because in the late 1800s, this was an easy area to work in ecology. And therefore, we know a lot about old field succession. Okay? All right, other types of succession. Well, another type here is called the inhibition model. in an inhibition model, you start out with a particular sear in a community that progresses in a particular way through multiple sears. This is our classic facilitated succession model. In an inhibition succession model, this is possible. This part here is facilitated succession, and this part here is the inhibition. The idea in inhibition is that one or a few species by chance move into the community, and when they do, they block the normal facilitated succession model. So instead of the F here promoting the growth of species in sear C, they block it. So you get this weird kind of blocking of the rest of facilitated succession simply because of the arrival of one or a group of species. So if we play around with the old field succession model, the model would work like this. If this is our old field at the top, Erigeron annuus, and we have that species here too, it's an herbaceous species. So there's Erigeron annuus, called daisy fleabane. It promotes the growth of the next group of species, right? The woody species leading to the shrubs and the trees, etc. With Erigeron and the colonization of Erigeron, we preserve the facilitated succession model. On the other hand, if this species here, Ceteria, shows up, and we have Ceteria faberii here as well, both of these species occur in Pennsylvania, Ceteria blocks Erigeron. So if Ceteria moves in, Erigeron can't, and that means that there's no prepping of the area environmentally for the arrival of the subsequent species. So Ceteria, this giant foxtail, this is as far as you get. So I could end up with a field of giant foxtail and never get to trees. This would remain as effectively a grassland. Okay? That's the inhibition model. A species inhibits other species that would normally move in from moving in. Okay? All right, next one. Transient climax. All right, in this model, it works a lot like facilitated succession. I have a species that comes in here, but instead of this community, community E, remaining in perpetuity, it also disappears. And when it disappears, the system shifts back to the original sear. So transient, meaning it doesn't last very long. One of the best examples of this would be a seasonal model. So let's take Presque Isle Bay. I think that would be a good one to talk about since we all should be pretty comfortable with Presque Isle Bay. Presque Isle Bay, in the spring, when the ice melts off and the light comes back, you get a group of photosynthesizers that their life cycle is timed so that they show up in the water in the spring. Okay, so you get some algae that have this diapause portion of their life cycle where they're not active, right? They're in this kind of quiescent state waiting for day length to increase again. As soon as the day length increases, they become more active metabolically and they start doing their thing. You also have other groups of species who are also timing their arrival based on day length, because if I'm a zooplankton, I better not arrive and come back from my diapause portion of my life cycle, I better not do that in January. There's going to be nothing for me to eat. So other species are going to begin to show up later in this model. The algae present facilitates the zooplankton because the zooplankton eat the phytoplankton. And then we have groups of zooplankton that feed on other zooplankton, right, et cetera, et cetera. And what I've got in the seasonal model is a planktonic community. This planktonic community develops over time. I would expect there to be different species of algae and zooplankton at different times of the season. The algae that shows up in March is not the same set of algae that shows up in August or September. The bay is changing in temperature. Some of these algae are better adapted for different temperatures. So I would expect certain algae would begin to go into their diapause portion of their life cycle, same thing with some zooplankton, whereas other zooplankton would begin to show up later on because there are more warmer water zooplankton. And I would get this orderly progression in species composition of these seers based on day length and temperature in the bay. Now, once we get over here to kind of this climax community that does really well in the bay in late season, at some point the weather gets bad, these species begin to drop out of the community, they go into diapause, that resting stage, and then we kick back through here, and then next spring we start all over again. I would expect this regular change in species composition in the bay based on the time of year. This is a transient climax model. I can't stay at this part of the model because I got to move through the winter time. Well, that kicks me back to these other species that start things out in the spring. Another example would be a lion kills a gazelle, and then that lion begins to feed on the gazelle, and at some point their mouth parts are too big to get any nutrition out of the gazelle anymore. They're sated, and then I would get a group of hyenas that begin to move in. They do the same thing. They finish feeding, and then a group of buzzards begin to move in. They get all the nutrition they can out of what's left of the gazelle. And then I also have all these microorganisms that are beginning to colonize, right? I get insect colonization, and eventually the gazelle is gone. There's nothing left of it, right? At which point I reach the transient climax stage and I'm done. The next time a gazelle is killed by a lion, we start the successional process over again. This regular change in species composition makes it a successional model. Okay? That's transient climax. All right, and then one of my favorites here is the cyclic climax model. In a cyclic climax model, we have the initial seer composed of a group of species, followed by B, a group of species, and then maybe C, and then we're back to A again. So the community basically cycles through these species. Okay, so here's our example here. We're in Scotland in the dwarf heaths. There's a lot of wind there. You don't get species that stick up very high in the air because of all the problems that wind brings. The wind is blowing in this direction from right to left. The wind is blowing, and then we have three things that we're keeping track of. One is this species called Kaluna. Another species is sandberry here, and then there's bare area. Okay? Actually, I've switched them. Sandberry, Kaluna berry area. Sorry. Okay, Sandberry and Kaluna are both species. Bear area is obviously no species. All right, so the way this works is Kaluna is actually doing the colonizing. So Kaluna can grow pretty well on these heaths. They can take the wind okay, in part because of their growing strategy. If the wind is growing in this direction, what the Kaluna does is it begins to grow out like this. It's one of those clonal plants. It sends out a structure to put up new material in this direction. In the meantime, the wind is blowing around a bunch of sand. You're sand blasting the plants that exist in this area. And as you do that, you begin to kill off the parts of the plant that are exposed to the wind. These parts are on the lee side. They're not being exposed to the wind. That makes sense? Okay? So what you end up with here is all this dead material from the Kaluna that's dying as a consequence of wind erosion. The Kaluna is staying alive by growing away from the wind, right? It's always keeping itself on the lee side of itself. Okay? Now this other species, Sandberry, is playing the same trick, but it uses Kaluna to block the wind. So Sandberry seed gets here, establishes, and then it puts up plant material, and it also grows in this direction. So what you get is Kaluna moving, right, growing in this direction, eroding in that direction, and then Sandberry hiding on the lee side of Kaluna, and it also grows in this direction. Okay? Which means if you watched it, it would look like Kaluna and Sandberry are chasing each other across the ground, right? Because Sandberry has to stay ahead of the Kaluna, but close enough to benefit from the wind being blocked, and at the same time